Just 1 minute, sir.
Okay.
So let me introduce the speaker, Dr. Shyamal Gucchait. He is currently working as assistant professor in Department of Civil Engineering, NIT-Rourkela. He has done his bachelor's in civil engineering from Bengal Engineering and Science University, Shivpur. His MTech in structural dynamics at IIT Roorkee, and he finished his PhD in civil engineering at IIT Kharagpur. He worked as a structural designer for 2 years in the industry, and he also worked as a scientist at CSIR SCRC Chennai for 1 year, and he has more than 3 years teaching experience. Uh, his research areas are in structural dynamics, structural health monitoring of real-life structures, damage detection using deep learning techniques. He has 5 publications in international journals and 3 conference publications. He is guiding 1 PhD student. He has guided 5 MTech thesis projects. So I thank Shyamal sir for accepting the invitation, and I hand it over to you to present.
Thank you, sir. Thank you, Professor Gattu, for your nice introduction. So, can you hear me clearly,
Hi,
sir?
Professor.
Am I audible?
Yes, yes.
Yes, sir.
Oh, okay. So
Hi,
first I will
Mahindra.
share.
Sai Krishna,
Sai,
nice
please
to have you
be
here.
silent.
Nice to have you here. We have Shyamal sir, so we can listen.
No, today. Okay. Yeah, please proceed, Shyamal.
Yeah.
Actually, the first talk was supposed to be Subhajit sir, but because he has class, he has class.
Yeah, that's
so
what I
we
was
had,
thinking. There was a
Huh?
clash in the agenda or something. I don't know.
Yeah, we exchanged the slots. So yeah, so sir is present now. Yeah.
Sure, no worries. Please proceed. Thanks. Hello?
Hello.
Yeah.
Can you see it? The present.
It is coming, but yeah, it is loading up.
Yeah, it's visible.
Okay.
Yeah, visible, sir.
Okay. So myself, Dr. Shyamal Gucchait, I'll be presenting on artificial intelligence based structural damage detection technique. Okay. So the Professor Gattu has already introduced myself. Now the topic mainly it is on structural damage detection using AI. AI means artificial intelligence. Okay. So it includes different kind of optimization techniques also, like gradient based, ECE based optimization technique. And after that, I will discuss the CNN, means convolution neural network based structural damage detection. Okay. So one by one, I will discuss. Now, first of all, what is structural damage detection? So basically, we can do it in 2 ways. One is direct test by entity testing, like measuring means using different kind of instrument like ultrasonic pulse velocity test on concrete or impact hammer testing or different kind of GPR technique. So all those entity techniques we can perform on the structure, and we can find out the structural damage. The second thing, it is based on optimization technique, and that is the inverse problem. So inverse problem, it is related to optimization technique. How we can assess the characteristics of the causes concerning to some phenomena of some physical event. Okay, so doing the damage detections, we have to perform two things. One is forward problem, and second is inverse problem. Now, in the forward problem, you can see here an equation that is Ke into U is equal to F. So that is a very basic equation in structure, in the field of structural dynamics, or you can say the FEM also, that K is what? The stiffness, and E is the displacement, and AF is the force field. Now, in forward problem, what we solve? If we know the stiffness of a particular structure and the applied force, okay, so and we apply the boundary conditions, material parameters. If those things are known, then we can find out the unknown displacement field of the structure. Okay, say we can find out for a cantilever particular beam, if we applied a load at the cantilever end, we can find out the displacement. So that is the forward problem. Now, the inverse problem is what? If the force field it is known, okay, the displacement it is known, and the geometry it is unknown, or you can say the material parameter it is unknown. So how we can find out that? So that problem is basically the inverse problem. So for structural damage detection, we have to solve these two problems, forward problem and inverse problem. Okay. Now after that, I have already told you that structural damage detection problem, for doing that, we have to solve optimization, or we have to use the different optimization techniques. Okay, so it has a different real life application, like structural health monitoring of real life structures, biomedical elasticity imaging. You can see in this left hand side figure a bridge it is there. So we can always feed some sensors on the bridge, and we can take some real life data like acceleration or displacement data. Then after doing some calculations by optimization technique, we can detect the damage for a particular bridge or any kind of structure. In the right hand side figure, you can see an example of the application of inverse problem in biomedical elasticity problem. Means here you can see here that a tumor it is detected from this background figure. So the background figure it is for the soft tissues, okay, and hard tissue it is indicating the tumor, and it is indicated by the blue color. So with this kind of optimization technique, we can find out where we can solve this kind of problem also. And other field also are there, like seismic exploration, or a lot of things are there. Now there are two kind of techniques, inverse identification techniques. One is traditional verification techniques like visual inspection and non-destructive test. About non-destructive test I already described. Okay. The second is how to find out, or how to do the condition assessment of the structure, okay, using non-traditional techniques. In non-traditional techniques, a lot of things we can do. Here I have described only two things. One is image-based structural damage detection, and second is vibration-based structural damage detection. Okay, so we'll discuss both these two. Means we'll discuss here with some examples also, how to do the damage detection, or how to solve the damage detection problem using image as well as the vibration data. Now, in this slide, you can see the classification of inverse identification techniques based on artificial intelligence. Means what are the different kind of algorithms are available in optimization framework such that we can do the damage detection. You can see from this flow chart that inverse identification techniques can be broadly divided into conventional optimization methods, and second is the artificial intelligence based algorithms. Okay. In conventional one, I think you have already know these things, that there are a lot of algorithms like direct search method or simplex method, And second is the second category of the conventional technique like gradient based method, or in the gradient based technique also there are a lot of variation like Gauss-Newton method or quasi-Newton methods. So these methods are very old. Okay. And the new things which came up in this field of structural damage detection, that is the artificial intelligence based algorithms. In AI also, AI is basically what? That intelligence of machines or computer. Okay, not the human intelligence. And with this intelligence of machines and computer, it has applications in different fields. So in this structural damage detections also, we can apply the artificial intelligence technique using different kind of algorithms like machine learning technique, neural network, deep learning. All those are the subclasses of artificial intelligence based algorithms. Now, structural damage detection. What is the damage? Okay. So damage can be identified by the deterioration of the structural original material property or geometrical property. Like say for a steel structure, if corrosion happens, so that we can call as a damage. Or for concrete, if some cracks developed or there is reduction in the strength or stiffness for a particular beam, or say for column, any kind of member, so that thing we can call as a damage. Okay. Now, what are the stages of damage detection technique, or what are the means there are 4 steps of damage detection techniques we have to follow. First is finding out the existence of the damage. That means first we have to find out that there is damage or that the structure is undamaged. That is the first question. Second is the locate the position of the damage. Means we have to locate the position of the damage. Third is quantification of the damage. Quantification means we have to estimate that what is the crack or length of the crack, okay, or how much depth it has happened. So that is the quantification procedure. And fourth is the remedial measures. Means like the examples, one example for remedial measure like retrofitting technique. We can use retrofitting technique and do the some means corrections actually. Now we'll discuss these first 3, that finding out the existence of the damage, finding out the location of the damage, and third is the we will quantify the damage, means how much damage it has happened in the structure. Okay. The fourth one we will not discuss. So that is a different issue, that retrofitting or some kind of technique such that we can cover up those damages. Now, first optimization technique I'll discuss, that is called the gradient based optimization technique. In gradient based optimization techniques, you can see here some equation. Actually, this is the cost functional. In every optimization technique, there will be a cost function and some criteria, like some upper limit, lower limit, those kind of constant will be there. Okay. So here in this gradient based techniques, we have to optimize this cost functional, and that is basically the error between the computed displacement and the measured displacement. Here U is the displacement. U is the calculated displacement and UM is the measured displacement. So basically we are calculating the error of the calculated and measured displacement and minimizing that with this cost function. Okay. And we'll be having some constraint. So in gradient based techniques also, there are different kind of techniques like Gauss-Newton method, quasi-Newton method. So all these techniques are there, and another technique is quasi-linear technique. Okay. So all these methods there are, but the main disadvantages of this gradient based techniques or gradient based methods is their non-convexity and sensitivity to initial guesses. Okay. Means if we start from different initial guesses, the algorithm will converge to different point. We cannot find out the global optima or minima. So that is the difficulty for this gradient based optimization techniques. Now, an improvement over the gradient based technique, it is the development of error in constitutive equation based approach. Okay. So I have done detailed research in this field using this ECE technique, or that means error in constitutive equation based technique in my PhD work. So basically it is defining the error between the a stress and the strain terms. Okay, the stress will be calculated from the numerical data, numerical model, and this strain, it is dependent on the measure displacement data. And we will find out the error between these two. Then we will minimize this cost function like the gradient based method to calculate or to find out the our damage area. Okay. But you know that in all of structural damage detection technique, if we consider any measurement data, there will be some error in the measurement data. So in case of erroneous measurement data, if we use the error in constitutive equation based approach, there will be some problem. So here, what I have done, I have added a additional, you can say cost functional, a term in the cost functional, which actually it is defining the error in the measurement. Okay. And we have used the penalization technique to solve this problem. One important thing to notice here that this MEC, we call it as a modified error in constitutive equation based approach. If we add these two terms, and is MEC will converge to EC problem is if alpha tends to 0, and it turns to L2 minimization, means least square method, if alpha tends to infinity. So this MEC functional will also means we can apply it when there is an error in the measurement data. Now, one previous form of the MEC techniques was available, proposed by Banerjee 2016. In my PhD work, this is actually a coupled equation. So for large structure, to solve this equation, it will be very difficult. Okay. So in my PhD work, what I have done, I have uncoupled these two equation, and because of that reason, the computational cost was very it was reduced. Okay. And I have solved it, means with that I have solved some damage detection problem. One example I will tell you, that experimental validation of the damage detection procedure using the EC for isotropic aluminum plate. Okay, so here the data was taken directly from the testing. Okay, so what I have done here, you can see here, this is an cantilever aluminum plate. Okay, and in means damage was introduced into this plate by taking some thickness of that plate. Okay, so that means if we take some thickness of this plate, you can assume it as a corrosion. Okay, if the thickness is reduced, that means damage has happened, means stiffness has reduced and damage has happened. Now, what I have done here, I have used here impact hammer testing. Okay, so this is called a dynamic testing, and I have performed that experiment with this dynamic testing performed by this Bruel and Kaiser that instrument. Okay, and Emiscope software was used to calculate the natural frequencies and mode shapes. So from this figure, you can see here that the whole plate, it is divided into lots of nodal points. Okay, and for each point, we have to find out the FRF, frequency response function, for the each point. Okay, by doing this impact testing. And if we calculate the FRF of the each point, then then from that we'll actually do the some analysis by this Emiscope software, and we can calculate easily the natural frequencies and the mode shapes of a structure. So actually that analysis, it is the free vibration problem, solving the free vibration problem. Okay. You can see in this figure that the left-hand side figure, it is the third mode shape of the damage plate. It is the numerical one, and in the right-hand side, you can see the experimental figure, what we have got from this taking the experimental data. Okay, and regarding the natural frequency, you can see the experimental natural frequency, third natural frequency was found to be 142 hertz, and numerical it is 155 hertz. So there is some error. So obviously for practical, if we do some experiment, there will be some error. Okay, and from the numerical from the mode shape plot also, you can see there is some zigzag or some error. It is there for the experimental mode shape, third mode shape. Okay, so what I have done, I have used only one mode 7, one natural frequency to find out the damage of that particular plate. Okay. And using that ECE method, you can see we have reconstruct those figure. Okay. So we have actually, this is the left hand side figure. It is actually the reference figure. And for different two cases, you can see that how that ECE algorithm was successful in detecting the position. Okay. And as well as quantify the damage. Okay. Means we can identify the thickness, how much reduction has happened due to the corrosion or the damage. Okay. Actual damage of that structure. Okay. So it was successful and within very less iteration. So computational cost was very much reduced compared to the traditional MEC algorithm. So this is a particular experimental validation of the procedure. Some other means numerical applications was also there, like for composite plate or for means application in the biomedical field also. But here I have not discussed. Now I'll discuss a separate thing. Separate thing means all the thing means it is related to structural damage detection with inverse optimization techniques. Okay, but here I will be using the damage that deep learning technique. So deep learning is what? Deep learning, it is a specialized form of the machine learning, which is essentially a neural network with 3 or more layers. You can see in the neural network, means I think you have already seen it, means the diagram of neural network. There will be some input layer and output layer will be also there, and some hidden layer will be there. So each layer will be connected by some nodal points, and those nodal points are called the neuron. Okay. Basically, neural network, it is resembling the human brain. Okay. These neural networks attempt to simulate the behavior of the human brain, and in deep learning workflow, relevant features are automatically extracted from the data. That means the deep learning is having a special capability of extracting the automatic features from the data. If we have some real life data, deep learning can identify some automated features. I mean, automatically it can identify some important features from those data. Okay. So that is the special advantage of the deep learning compared to the neural network. Neural network cannot identify automatic features, but deep learning can. And CNN is actually the full form of the CNN is the convolution neural network. It is a special kind of multi-layer neural network. Okay. So it is a particular kind of deep learning technique, and it is used to recognize the pattern directly from the images or the signals with optimal pre-processing. Means if we have some image data or some time domain signal data, we can use the convolution neural network, okay, to classify the things. See here, if this figure here, it is describing means the different components of the CNN. We have some input image data, then some layers, convolution layers will be there. In convolutions layer, there will be two main operations. One is convolution, another is pooling. Okay. Then after that, there will be fully connected layer. And in fully connected layer, actually it is consist of ANN, artificial neural network. So lot of layers of ANN will be there in this fully connected layer. And after that, it will be related to the output class. Okay, so an output class, it is means for our case, that output class, it is divided into two parts. One is cracked or uncracked, means we have to check that that our structure is cracked or uncracked. Okay, if we have some given input images or signals. So this is the basic structure of the CNN. We'll be having input data. We'll be having some convolution layers, then fully connected layers, and after that, the output class. Now, depending on the data processing, we can divide, or we can means we can have two kind of CNN. One is 1D CNN, another is 2D CNN. What is the difference between these two? That kernel, for kernel is what? Kernel is a small sample means of data, means it is a, by this way we can collect the data from the input sample. Okay, and kernel moves through over the data. Now in 2D CNN, kernel moves in two direction, in X direction as well as in the Y direction, or in the horizontal direction as well as in the vertical direction. But for 1D CNN, this kernel moves in only one direction. Okay. And this 2D CNN, it is used mostly for the spatial data, that is for the images, damage detection using the image. And 1D CNN, it is used for the temporal data, means the data like acceleration or for velocity, we can use the 1D CNN technique. The difference is basically the movement of the kernel in two way or one way. If it is moving in one way, then it is 1D CNN, the figure V. And if it is moving two direction, then it is 2D CNN. Now, we have used these CNN-based techniques for detecting the damages using some already data available for the concrete structure. Means this data, this SDNet 2018, we have taken from some journal papers. So they have data, means image file for the cracked and uncracked pavement, or for bridge deck, uncracked deck, or for some cracked wall. So all those image files we have collected from the source SDNet 2018. Okay, and 56,000 cracked and non-cracked images of wall, pavement, and deck was there in that data source. And then we means perform the CNN. Okay, first the training and validation. There are three stages of CNN. First is training, then second step is the validation, and third is the testing. So for first two step, training and validation, we have divided this whole data into different ratios like 50-50, 70-30, or 90:10. Okay, that means for the last actually 90:10, you can say the 90% image data was used for the training, and rest of the data, 10% data, we have to used for validation of the algorithm. See here, three different shallow deep learning technique, or CNN, we have used for detection detection purposes. The first is AlexNet, second is GoogleNet, and third is ResNet 18. All these numerical analysis have been done with MATLAB. Okay. Now you can see the performance, and we have used means data in different ratio, 50-50, 70-30, 90-10, means we have checked that in what ratio it is, the accuracy is means maximum. Okay, so you can see that if we change the ratio of the training and validation, the accuracy is changing. The bottom figure, the percentage accuracy versus the different training testing ratio, and that also for the three different algorithm, AlexNet, GoogleNet, and ResNet 18. So from this figure, you can see that ResNet and GoogleNet, it is giving the maximum accuracy, and AlexNet, the accuracy is little bit less, but more or less it is almost 90%. Okay. Say for AlexNet, all the things, moreover, it is very close to 90%, and for GoogleNet and ResNet, it is more than 93%. The second figure, it is for the also same thing, it is performed, but with for different image data set. Okay. Third, it is performed for the wall images. Okay. And same thing we have performed. And we can conclude here that from this analysis, we can conclude uh, before conclusion, you can see here this table, the computation time of different algorithms for pavement images. Means for pavement images, you can see here the computational time for different algorithm, which is required to solve the damage detection problem. For AlexNet, the computational time, it is 1/3 compared to this other two algorithm, GoogleNet and ResNet. Okay. The accuracy is little bit less, but the computational time of the AlexNet, it is less compared to the, when it is 1/3 compared to the GoogleNet and ResNet. So you can draw these conclusions that compared to the other two algorithms like ResNet 18, in this study, ResNet 18 achieves overall highest accuracy. So ResNet 18 has highest accuracy, but AlexNet is advantageous because of the significantly less computing time. Okay. So ResNet 18, it is having the highest accuracy for different cases. If you check all the cases, and AlexNet, it is requiring less computational time. Okay. With sufficient accuracy, you can say. So for the most practical damage detection problems, if we have some real-life data, image data, we can use the AlexNet, okay, using MATLAB, and we can detect the damage position using the image analysis, you can say. And after that, what we have done, the last thing. Now, after this, we have told means I have discussed about the training and validation. Testing we have not done, but you can see the testing procedure from this figure. The testing of cracked and uncracked pavement data using the AlexNet algorithm. Okay, so here we can say 28 figures are there. Okay, so for 20 different set of images, we have tried to check that any image is cracked or non-cracked. And at the top, you can see here the accuracy is also mentioned. Okay, see the first figure, it is written UP 98.4. That means it is uncracked pavement, means that our algorithm, it can told that it is uncracked with 98.4% of accuracy. Okay. So means for all the cases, most of the cases, we are successful in detecting the crack, but here only one unsuccessful means we have not detect the correct thing only for one unsuccessful case. Okay, say that this it is indicated with this color. It is showing here UP, means uncracked pavement with 59.1% accuracy. But this from this image you can see here that is not means some crack it is there. Okay, so it once false detection was there. So up to this we have discussed about the deep learning technique, or how to use the deep learning technique to detect the damage using the raw images collected from the actual structure. So that image can be collected from the any camera, digital camera, or it can be collected by using some drone. Okay. So with drone images also we can perform the damage detection analysis. Okay, but we can apply the damage detection technique and detect the damage location. Okay. And also can quantify the crack. So that procedure I have not discussed, but we can also perform some image analysis. Means we can directly, it is available in the MATLAB, so we can use that algorithm. Okay, and we can quantify the means we can calculate the number of pixels of particular crack location. So with that we can actually find out the crack length and the crack width. Now we'll discuss the next thing. We'll discuss about the how to use the 2D-CNN technique, or how to apply the 2D-CNN technique in detecting the damages of a real life truss or frame type of structures using time domain data. Okay. You can see here the flow chart of this 2D-CNN algorithm. The first we will load the data in the Google Colab. Here we have used the Google Cloud platform. In the Google Cloud platform, you can perform any kind of means you can write your own code in Python programming and you can run it. Okay, so what is the advantage of the using Google Colab is that we can use a huge amount of GPU processor and the RAM support from the Google itself. Okay, so we have used that Google Colab technique, and the fast step for this damage detection problem. It is the loading of the data in the Google Colab. Second thing is the creating list for signal input. That means the input and output data we have to level it. Third is splitting the data into training and validation set, like the image analysis. Then we'll be doing we'll apply the CNN, 2D CNN, or you can use also the 1D CNN, convolution, means 1D convolution neural network. The next thing, it is the evaluating the model. And after that, the prediction with the new data set. So you can see here a steel frame in the top picture. Okay. This steel frame, actually, this experiment was performed in the Qatar University using grandstand simulator. Okay, by Abdeljar et al. In 2007. We have collected that experimental data. It is it is easily available in this internet. You can also download it, and you can also check your algorithm's performance by using this data. Okay, so in this frame, steel frame, 30 joints are there. Okay, and for each joint, they have used means they have put an accelerometer. So 30 accelerometers are also installed on those joints. Okay, then what they have done, they have used a modal shaker to apply the vibration on the structure. Okay. And so now what we have 31 different means scenarios, structural scenarios we have. That means damage in the 30 joints. So that will be 30 case, and one will be undamaged condition. So total 31 scenarios we will be having. Okay. So first scenario corresponds to the undamaged case, and from the second to 31, we'll be having 30 damage cases. The question is how the damage is introduced in the structure. They have loosened the bolt for the each joint and introduced the damage for particular joint. Okay. Say I want to introduce the damage in the first joint. So then what I will do, I will first loosen those bolts at that joint. Okay, and then I will apply some that load by the modal shaker and measure the acceleration for all the points. Okay, so we are measuring the acceleration for all the points. We are introducing the damage at these joints one by one, but we are measuring the data, acceleration data for each joint. Okay. So we have used that, and you can see here that convergence loss and accuracy plot of this our proposed 2D CNN model. Okay, and in the right hand side figure also you can see here that convergence and convergence of loss and accuracy plot of the different model already it is found out by the Trang et al. Okay, so you can see here from this two plot that loss curve for our case it is reducing very fastly, and with only 8 iterations it is means we can achieve the convergency. Okay, and only you can see here the accuracy is almost 100%, more than 90% with the experimental data also. But for other algorithms, other CNN algorithms or other deep learning algorithms like 1D CNN or GRU, those techniques proposed by this Trang et al, you can see that more about 100 iteration it is required to converge. Okay, so for our case or with our proposed algorithm, at 10 epochs only, means loss for training and validation approaches to almost 0, and accuracy for training and validation approaches lost to almost 100% with our proposed 2D CNN model. Okay, and this comparison is made with our algorithms where it takes almost 100 epochs to converge, and also giving means also the accuracy is not reaching to 100%. Means all other algorithm is taking 100 epochs or iterations, but here our 2D CNN model is only requiring 10 epochs only. Now with that model, we have detected the damage for different damage scenarios. The first plot, the top plot, you can see that prediction accuracy, that blue color, it is showing the prediction accuracy. Okay, and the brown color, it is showing the actual value of the damage. So you can see for the single damage case, then in that figure, it is showing the probability of predicting the damage for the 2 location, then for the 3 locations, and similarly it is goes on 4, 5 locations, 7 locations, and for all the cases, our proposed 2D-CNN techniques was able to capture the damage positions means the accuracy was very high. Okay. And the false damage detection was also very less. Now we'll discuss the conclusion that I have already told you that proposed 2D-CNN model can automatically extract and learn the features from the unprocessed time series data, and it can accurately identify damage for the single and the multiple damage position. Okay. And for our case, the accuracy is very close to 100%, and it is taking very less number of iteration. That means the computational cost, it is very less. Now I'll discuss about the future research curve of this technique. So the first is the development of this deep learning technique in localizing and quantifying the damage for the concrete or steel structure using different raw image data. Development of the 2D-CNN algorithm for beam and truss or frame kind of structures, or for plate kind of structures. Okay, for single as well as for the multi-damage scenarios. The third is exploring the possibility of the application of 1D or 2D-CNN technique for detecting the delamination of the composite structure. So that is on a particular kind of failure in composite plate or composite structure, you can say. And fourth one is the biomedical elasticity imaging technique with the deep learning process. So we can also apply the deep learning, means this 1D or 2D CNN, in detecting the tumor or lumps in human tissues, also biological tissues. So this is the future research scope. Now these are the references, and thank you. So now if you have any question, you can ask.
Shyamal sir, thank
Yeah.
you for your wonderful talk. And I have one question.
Yeah.
In the aluminum panel free vibration testing you have done,
Yeah.
you have shown the third mode, and for the third mode you have given measure the frequency and the computational
Yeah.
frequency. Like, why is it that you're looking at third mode? Is there any reason?
Actually, see, for you can use the fast mode or second mode also. Okay, but if the higher number of modes it is used, then the accuracy or capability of the algorithm will increase. Capability in detecting the damage. Okay, because the higher mode, it is having the higher deflection curvature like that. So it will capture those behavior.
And when you say the error in constitutive equation, that sigma dot the epsilon, something like that, that equation.
Yeah, that equation.
What exactly?
Actually, it is the optimization function. You can say the cost function. Okay. So basically, we are finding out the error in the constitutive equation. This sigma we are calculating with the numerical data at the each iteration, and this epsilon we are calculating with the measured displacement data. Okay. So there will be the error between these two, and we are trying to minimize this error. Okay. So with using a technique here, so that technique, it is basically, we called it error in constitutive equation based approach. So it is solved by using Lagrangian functional approach. Lagrangian approach, you can say.
So like you have numerically obtained stress value and numerically obtained strain value.
Yeah, no, actually, yeah, numerically obtain the stress value. Okay. And this epsilon, that is the strain, we are calculating with the measured displacement data. Okay. So we are trying to find out the error between the calculated model and the numerical model. Calculated numerical model and the measured data from the data. Okay. The error between the calculated numerical model and the measured data.
Why don't we use numerical strain and the numerical experimental? Strain experimental, strain numerical.
Because if we use here the numerical means say in calculating the strain, if we use the numerical displacement, then the error will be zero for zero noise case. Okay, so
Yeah.
we are trying to minimizing the error between the numerical model and the practical real life measurement data. Okay, so
Means
that
what
is
I'm
our
saying
basic
is,
target.
numerical model, you can get strain value, right? Why are you calculating stress value?
Because see, means if we want to find out this error between the constitutive equation, so one term should be this sigma and another term that we are multiplying the strain with that constitutive relation. Ultimately we are converting into the stress. So basically there are two stress only. Okay.
So questions from the audience, you can ask. Sir, answer. Ipsita madam, you can, if you have questions, you can ask. Ipsita madam is from KIT Bhubaneswar.
Okay.
Purnachandra Pandit sir, I think he's writing Mahi MIT, means probably Pune,
Yeah,
MIT Pune.
nice presentation, sir. Regarding this artificial intelligence, actually, I am working on corrosion of reinforced concrete.
Okay.
So certainly, this technique, artificial intelligence, based on this damage analysis, now what you have shown. So I'll also slightly think on that matter because my research scholars are also working.
Okay, sir.
So we'll think it on that, sir. Very nice presentation, sir. I have some ideas also by listening your presentation. So that damage analysis and all.
Yeah, actually, if we have some measured data, we can always apply. Means actually
Yes, yes,
it is the data-driven technique. If we have some
yes, sir.
data, then we can apply it.
Yes, sir. Thank you, sir. In future, definitely I'll contact you, sir, regarding that
Okay.
AI, sir. Thank you, sir.
Okay.
Nirmala madam, if you are here, you can ask question. I think there are no more questions. So we will thank Dr. Shyamal sir one more time for his talk. And the next speaker is Dr. Shubhajit Mandal sir. He's available online now on MS Teams. So we will I will introduce sir, and sir, thank
Okay,
you
sir.
Shyamal sir.
Then okay, sir. Thank you. So I'll leave. Okay.
You can, if you want, you can be there. You can unshare the presentation.
Okay.
So Subhajit sir, are you here? I think probably he's online, but not at the laptop. But call him once. Oh, yeah. So, okay. So, sir is here. So let me introduce. Good evening, sir. Subhajit sir. So let me introduce Dr. Shubhajit Mandal. He is working as assistant professor in Department of Civil Engineering, NIT-Rourkela. He joined NIT-Rourkela in 2018. He has done his MTech and PhD in structural engineering from IIT Kharagpur. He has more than 5 years teaching experience. His research areas are in structural dynamics, construction materials for net zero emission, non-destructive structural health monitoring, and so many more. He has publications in 15 international journals and reputed conferences. He's guiding 4 PhD students, and he has guided 10 MTech thesis projects. His research work has been sponsored by SCRB, and he has done 6 industrial consultancy projects. As administrative positions, he's currently assistant warden in a hostel, and he is also a lifetime member of the Institute of Engineers India. So I welcome you, Dr. Mondal sir, and I request you to please take over the meeting and present your talk. Sir, we are not able to hear, sir. I think you were being muting it, sir. At least I'm not able to hear. So. We are not able to hear. No, we are not. We are not getting the voice.